In this video, we're going to look at PageRank, another very popular centrality measure, and also its variation called Personalized PageRank, which can be used to personalize recommendation for graphs. So PageRank was originally invented by the founders of Google, Sergey Brin and Lawrence Page, and it was published back in 1998. And this was also one of the first algorithms that they used to rank web pages. The problem that PageRank is trying to solve is to try to rank all the web pages on the web. So that means that given the internet, let's say, as a directed graph, so we have directions because one web page can link to the other, but may not be vice versa. And given this graph, we want to find its most interesting or most central node. And the intuition that it's using is that we say a node is important or interesting if it's connected with other important nodes. So here we notice that it's a recursive definition, but that's OK, because intuitively it makes sense. And the more important thing is how do we leverage this intuition and actually compute a score numerically. So the proposed solution is to use the random walk model. So in this random walk scenario, it means that the most popular nodes are the ones that have the highest steady state probability, or SSP. So what does that really mean? Is there a more easy to understand way of figuring this out? So you can consider, let's say, we have like a random walker, like a person whose whole job is to click on web pages on the web. So now we give this person, this random walker, the whole internet. And we will allow this random walker to start with any node in the graph and allow it to do what we call random walk. So that means this person, the only thing that he or she would do is he would visit a web page, any of them, and then he would flip a coin and to decide to go to any of his neighbors. So in this example, let's say I start with node 1. So I'm the random person. And I will flip a coin and determine which is the next page, connected web page to visit. In this example, there's only one way, because 1 is pointed to 2. So there's only one way to go. So that means I'm surely going to node 2. And now at node 2, again, I will flip a coin and decide whether to go to node 3 or node 5. So equal chance here. I could go to 3, go to 5. And I will repeat this process for infinite time. So that means if I keep walking again and again for millions of years, then in the end, what you will be able to compute is the probability, or specifically what we call the steady state probability of finding myself on node number 1, probability finding myself on number 2, number 3, and so on. And these probabilities will also become the PageRank score. So in this example, state means web pages. So how do we compute this steady state probability? So remember from linear algebra class, one way is to first construct the transition matrix. So in this example, we have 5 states, or 5 web pages. So that means we construct a 5 by 5 transition matrix, where the number of nodes equals the number of rows and number of columns. And also, you notice that this is what we call a transpose column normalized matrix. So it's transposed because the columns are where the nodes are from, and the rows are where the nodes are going to. So for example, for node 2, it has 2 possibilities. So either go to node 3 or node 5. So that means for column 2, we'll have a value in cell number 3 and cell number 5. And it's column normalized so that these 2 numbers add up to 1. So that means there's equal chance of going to node 3 and going to node 5. And remember from linear algebra class, and to compute a steady state probability, you use the formula BP equals PP. Can be anything, actually. It doesn't really matter. You can solve for P exactly by doing an inverse. So another way to interpret that formula you just saw is that essentially we're computing P, which is the eigenvector that corresponds to the largest eigenvalue of our adjacency matrix. And that highest eigenvalue is 1 because the matrix is column normalized. So in other words, given the graph, you were able to construct this transition matrix, which only need the nooks and edges in the graph, we will be able to compute the steady state probability, which is all stored in the vector p. So a question that you might have is, why would such a p exist? So the actual theorem that's shown that it's guaranteed to exist. So it exists as long as the matrix is n by n, which is, for our case, number of nooks, number of nooks, and number of columns and rows are the same. As long as that matrix is non-negative, which also satisfies, right? Because that's probability of going from one nook to the other, which is guaranteed to be non-negative. And the third one is irreducible. So we haven't really discussed this yet, but we are going to very shortly. So what this theorem says is, as long as all these situations are satisfied, then we're guaranteed to be able to find p, which is great. So now we can do a quick recap before we show you the full algorithm of PageRank. So the model that we're using, or intuition that we're using, is that we're trying to imagine a person randomly moving along the nooks and the edges in the graph. And a nook's PageRank score is the steady state probability of finding that random walker at particular nooks. So we're able to compute the scores for all nooks in the graph. So previously we mentioned that p is guaranteed to exist if it's an n by n matrix, non-negative, and irreducible. And we haven't talked about irreducible. So which also means we need to figure out how to make that matrix satisfy that condition. So in practice, that's actually a very intuitive way, which also would help us understand a scenario, or to handle scenarios whether the random walker may get stuck in a particular part of the network. So imagine the graph have two connected components. So that means there's one subgraph where there's no edges connecting the other subgraph in the network. So imagine you are a random walker starting in one of such subgraph. Then there's no way for you to go to the other subgraph, right? Because all that you can allow to do is to follow links. So that since there's no link connected in the subgraph, there's no way for you to jump. So intuitively, that means we need to solve this problem. And to solve this, we want to introduce occasional random jump to any node. So that means instead of only following links, now our random walker also have the options of going to any nodes, like teleporting to any nodes in the graph. So it turned out that by implementing this occasional random jump, it also makes the matrix irreducible. So now we can look at the formal definition of irreducible. So it means that from any state, in our case, any node, there is a non-zero probability of going to any other state or any other node. So which essentially means there's the random jump or teleportation that we allow the random walker to do. So now we can look at the full algorithm. So here in the formula, what you see is very similar to what you previously saw, which is p equals bp, which we know we can solve it exactly by using inverse operation. So the only new thing that we added is the constant called c, or specifically 1 minus c. So 1 minus c, we called it the fly-out probability, or we mean the teleportation probability for the random walker to go to any random node in the graph. So that means the left part of the algorithm, which is c, constant c, times bp, that is what we have been doing when we're doing link following. So that means that c probability of just doing link following. And now we also have add the alternative, which is 1 minus c over n, and it's a number of nooks, and then a all-one vector. So this part may look a little scary, but this is actually just a vector with all the same value. So specifically, once you remove n inside that vector, all-one vector, essentially that means all values are 1 over n. So essentially that means there's a 1 minus c fly-out probability of using this 1 over n vector. And that means you have 1 over n probability of going to any of the nodes with equal probability. So that formula is actually also a very scalable way to compute a PageRank for large matrices or large graphs. So it can scale to billions of nooks and edges. And To compute this, we are essentially using the power iteration method, which you probably already learned in a linear algebra class. So what that means is we can iteratively apply the algorithm again and again and again. For example, in iteration 0, what we do is we initialize the vector p, which is on the right-hand side, to anything you want. So it can be a random vector as long as it's not 0. So a very popular way is to initialize it to all ones. Another way is to initialize the values relatively proportional to the degree of the node degree. And with that p vector initialized, then you just apply the formula to the right-hand side, which will give you a new vector p prime to the left. And what you do then is to move the vector p prime to where the vector p is. So that's your second iteration. And this second iteration, you do the same thing. You apply or you multiply p prime with the matrix B, and then you also add the 1 over n vector. And then you will get a new vector, which is p prime prime. And that's your third iteration. So it's just keep doing this. And eventually, you notice that the vector no longer changes. The p prime prime prime, for example, they no longer change. So this is the case where we say the algorithm has stabilized. So it's guaranteed to stabilize, so which means you can just run it for many iterations, and eventually you have the PageRank score for all the nodes in the graph. And in practice, for large graphs, you actually don't really need to run that many iterations. For example, you can just run 20 or 30, and you notice that the PageRank values don't really change it that much anymore. So if you really need to compute the PageRank algorithm, it's good to be able to do sanity check. So that means to check if your algorithm is running correctly, is it giving the right values. And to do that, I highly recommend going to this interactive PageRank demo, where you can create arbitrary graphs. So you can create a toy graph, for example, putting in the node, putting in the edges, connecting them. And you can immediately see the PageRank values. Here is the white text on the black background. And also, you can adjust the fly-out probability too. Here, they call the damping factor. So a very nice thing about PageRank is you can run it on any graphs you want. So all you need are the graph edges. So for that reason, you want to keep this as part of your algorithm toolbox. And generally, it's better than degree essentiality, because degree only consider neighbors that are directly connected to the node that you're looking at. While for PageRank, actually also connect a longer range relationship, for example. You can look at maybe 2 steps away, 3 steps away, and aggregate all that information. And in practice, it's also really great for large graph, because the runtime is linear in the number of edges in the graph. So that means it can scale to billion graph. But it does have a shortcoming, which is also why that Google these days do not only use PageRank, but actually a combination of many algorithms. So specifically, we can do something called Google bomb. So that means how do we mislead the PageRank algorithm? So one way to raise the PageRank score of a node is to create a lot of fake nodes in the graph and have all of them point to the node that you want to raise the PageRank score for. And if you look at the algorithm again, so having more vote going into a node can help increase the PageRank score. So you may notice that for PageRank, no matter who run the algorithm, we get the exact same PageRank score values. But intuitively, that doesn't quite make sense, because let's say you want to do ranking of web pages, then maybe I am more interested in, say, a sports website, while you may be more interested in, say, news website. So that means not all web pages are equally relevant to me or to you. So how do we adjust the PageRank algorithm so that we can rank pages such that the more relevant pages to you may be ranked higher? So fortunately, we only need to make one small change to the PageRank algorithm. And specifically, all we need to change is the vector, the all-one vector. So this is a reminder of what we saw previously, where the red vector is the all-one vector, And that is also the reason actually why we get the same PageRank scores no matter who run the algorithm. So now that suppose we want to compute this relative PageRank score or personalized PageRank score for you, where you are only interested or mostly interested in sports websites. So what do is then, instead of using the O1 vector, we change that vector to 0, 1 vector, or actually 0 plus some other values that not 0. So what that means is that you will put a 1 or non-zero value for the nooks that you are more interested in. You don't need to put the value for every web page that you know about. So you only need to put that for a small number of sites. For example, let's say I'm interested in news websites. So I might put a 1 for, let's say, New York Times, and other 1 for like Wall Street Journal. And what that means, or how that affects the algorithm, is that when the algorithm is about to do the random jump, now instead of jumping to any node in the graph with equal probability, now it has a preference. So we would more likely jump to the nodes that are news websites. And we also here use the notion that news websites tend to be more likely to be connected. So that means by putting a 1 on, let's say, Wall Street Journal, or put New York Times, that also means that the more chances that the random walker not only has a preference to jump to those websites, also more likely that the random walker would go to the other related news website that I haven't put a 1 at yet. And the reason we want to learn personalized PageRank is that you can use it for recommendation. So imagine the case where you apply personalized PageRank to rank products. So let's say you're Amazon and you have a customer product graph. And you're a new customer to Amazon and you have purchased 1 or 2 products. So by constructing a bipartite graph connecting a product with a customer that has purchased it, then you can put a 1 essentially in this graph, in this bipartite graph, and on the product that you have just purchased. And now you run the algorithm, the personalized PageRank algorithm. And after you run it, then you will be able to find the scores for the related products, meaning the products that many other customers probably also purchased, like besides the ones that you have bought. So this is a very generalizable technique, because you notice that we only need the graph structure. We don't really care how you construct the graph. As long as the graph edges, you can compute the personalized PageRank score. So this is also a great way for helping to visualize graph too. So meaning, instead of visualizing every single node, every single edges in the graph, now suppose you're able to get some feedback from the user as to what is interesting. So that means you can put the 1 on those nodes, and then you can run the PageRank algorithm, personalized PageRank algorithm, and you can get a ranking very personalized to a particular user, and you only visualize the nodes and edges where the nodes are the ones that have the highest score. So in fact, personalized PageRank is one of the big classes of algorithms. Generally, we call them diffusion-based or Gilbert association-based. So Gilbert association, that means things that are connected are more likely to be related. So personalized PageRank, another name for it is called random walk restart. And in another domain, let's say human-computer interaction or HCI, they also called a spreading activation or degree of interest. You'll see that powerful techniques like PageRank or personalized PageRank, actually they have been used in many domains and often under different names. And also in the next video, we're actually looking at another example where using another algorithm called belief propagation, which can do something very similar to personalized PageRank. So belief propagation is another powerful algorithm where it's not only able to do recommendation, also it has been used in a lot of different applications, like say fraud detection, doing image segmentation, correcting errors in codes, and etc. And all these algorithms are really popular because they tend to be very intuitive to interpret. They use this network effect and homomorphy. Then also very easy to implement. And the math is relatively simple. For example, for PageRank, it's only 1 formula. And Implementation is essentially just doing matrix factor multiplication, a few of them. And in practice, they're also very fast to run. So they're linear to number of edges. So that means they can scale to a very large graph. And also very nicely is that they often have probabilistic meaning. So that means not only like empirical ranking, but also you can interpret the scores probabilistically. In this video, we learn about PageRank and its personalized variation. And both are very popular because they are easy to understand, easy to use, and also scale to very large graphs.